Okay, so we're going to move into the world of redox, and we're going to start that with a little bit of a review. Today there will be a review of, first of all, what redox reactions are, how to determine oxidation number. You'll also see a video on how to determine what oxidizing and reducing agents are, and a video dealing with the balancing of a redox chemical reaction. Which is a little different from balancing a regular chemical reaction. Then I'm thinking of Wednesday's probably going to be an introduction to electrochemistry, probably enough that we'll be able to calculate cell potential, but maybe not a whole lot further than that, and we'll see what that looks like. So we're going to start by looking at this chemical equation here, where we have chlorine gas reacting with copper. Hopefully you covered this in Chemistry 110 or your chemistry class in high school or whenever you've had it, so this will be a review. But this is what we call a redox reaction, where instead of a proton being exchanged like in an acid-base reaction, instead we have electrons moving back and forth between different reactants. And we're going to give those special names, oxidizing and reducing agents. And so in this particular reaction, the copper is going to give electrons to the chlorine gas. And whenever copper gives electrons to the chlorine gas, it's going to cause the chlorine to gain those electrons. And when chlorine gains electrons, that's a process that we call reduction. In this case, we can see the chlorine is gaining 2 electrons. To produce 2 chloride ions, and then the copper is giving those electrons, or those electrons are produced in the reaction that copper undergoes, where copper is oxidized to produce copper plus 2 ion plus those 2 electrons, and we call that oxidation. Now those 2 reactions that you see there are actually not full reactions, or what we're going to call half reactions, and those 2 half reactions combine or add together to produce that reaction at the top. So just like we have an acid, we have to have a base around to take the proton from the acid. If we have a reduction process where something is gaining electrons, there has to be something that's producing electrons around in that particular reaction. So those 2 things are coupled together. So we have those half reactions. Now, one way that you can remember oxidation versus reduction is that oxidation is the loss of electrons, while reduction is the gain of electrons. You also see this other mnemonic device called Leo the Lion's goes grr, or says grr, where it means loss of electrons is oxidation and gain of electrons is reduction. And I can't emphasize how important it is to have those 2 things straight in your head and have a comprehension of those things. So important that you can decipher between oxidation and reduction. Now, how do we determine whether a reduction process or an oxidation process has happened? Well, we're going to have to use something called oxidation number, and that's what we're going to move to next. But before we get there, it's important to understand that, chemists give all sorts of different names. So we may say chlorine is reduced and copper is oxidized in this particular reaction. However, by being reduced, the chlorine is causing the copper to be oxidized. And when the copper is oxidized, it's causing the chlorine gas to be reduced. So we can call chlorine the oxidizing agent. It's reduced, all right, but it's oxidizing the copper, so we call it the oxidizing agent. And copper is being oxidized, but it's causing the chlorine to be reduced, so we can call the copper the reducing agent. An easy way to remember that is, if you can figure out which is oxidized, whatever's being oxidized is going to be the reducing agent, and whatever's being reduced is going to be the oxidizing agent. So if you can figure out what's oxidized and what's reduced, then you can figure out or determine, all right, what's going to be the oxidizing agent. Now, how do we keep track of that? We're going to use what's called the oxidation number. And the oxidation number is going to tell us roughly how many electrons that particular species has gained or lost in a chemical reaction. And generally, when we go through and determine oxidation number, we'll determine for everything in the chemical reaction that we're looking at, the redox reaction. So if we look here at chlorine going to chloride ion being reduced, each chlorine atom is going from a 0 oxidation number to a -1 oxidation number. Notice that the oxidation number is getting smaller. It's reduced, and so that's a reduction process. Now if we look at the bottom, the oxidation half reaction of copper to copper +2, each copper atom is going from a 0 oxidation number to a +2 oxidation number. So how do we figure out those oxidation numbers? That's going to be what we're going to focus on for the rest of the lecture, but I do want to talk first about what did I want to say? There was something that I was going to say that I felt like was important to talk about. Yes, notice that the oxidation number goes from 0 to +2. Notice it's getting more positive or getting larger. All right, whenever the oxidation number gets larger for an element in a chemical reaction, we call that oxidation. All right, so reduction, oxidation number gets smaller, oxidation number gets larger or more positive. All right, so there are some elements that have very predictable oxidation numbers. This should be somewhat familiar to you simply because some of these are the charges that these particular elements would have on the periodic predicted by the periodic table. So for instance, lithium, sodium, potassium, whenever those are in a compound, all right, those alkali metals are in a compound, they're always going to have a charge of +1. We predict that on the periodic table because you predict the charge of lithium, sodium, potassium. When they're in a compound, it's ionic. When it's ionic, they're an ion. When they're an ion, they're a +1. We know the alkaline earth metals, beryllium, magnesium, calcium, that whole family. When they're in a compound, they're going to be +2. When hydrogen's in a compound, hydrogen is in a compound, it's almost always going to be a +1. All right, now notice we're talking about these things when they are in a compound. All right, oxygen, when it's a compound, almost always going to be -2. Now, when I say hydrogen's almost always +1 and oxygen's almost always +2, there are, of course, exceptions to this. All right, oxygen doesn't have to be always -1 in a compound. In hydrogen peroxide, oxygen would be a -1. But we're going to assume, all right, that oxygen's going to be a -2. All right, we're going to assume that hydrogen, when it's in a compound, is going to have a +1 oxidation number. All right, now I want you to notice, all right, metal ions, normally positive oxidation numbers. All right, we said metals almost always like to be cations. They like to be positively charged. So they're going to normally have positive oxidation numbers when they're in compounds. All right, nonmetals, all right, almost always going to have negative oxidation numbers. Now, there's some caveats to that, all right? And as I said, there are almost always exceptions to these kind of things. Nonmetals, when they're in ionic compounds, are always going to be negative. All right? Nonmetals, when they're in covalent compounds, all bets are off. So we're going to see cases where nitrogen could be a -3, and we're going to see cases where nitrogen could be a +5. All right, and that's just how it works. It depends on what element they're in a compound with. All right, now elements in their elemental state, they're going to have an oxidation number of 0. So you might have noticed how I was qualifying everything by saying, all right, these elements, when they're in a compound, this is what their oxidation number is going to be. All right, that's because when the elements are in their elemental state, they have an oxidation number of 0. And when we talk about the idea of elemental state, all right, we mean like normally, for most things, that would just be the element just sort of hanging out by itself as an atom. So silver, right there in that particular example, silver as a solid, it technically could be silver as a liquid or silver as a gas. As long as there's no charge to it and it's not an ion, its oxidation number is going to be 0. That's what we call the elemental state. It's as it is as an element. Then at the bottom we have N2, and remember that nitrogen is one of those elements that exists as a diatomic. All right, so it's N2. And so when we see N2 in a chemical equation, right away, an alarm bell needs to go off in your head saying, okay, that's the elemental state of nitrogen, so its oxidation number is 0. All right, so element in their elemental state, oxidation number of 0. I will tell you, I get questions about that all the time from students. They'll be like, well, I'm not sure what to do with silver here. All right, so look at silver. What's the charge of silver right there? It's 0. It's neutral. So its charge is 0. Its oxidation number would be 0. For some of the others, like nitrogen, you're just going to have to know that nitrogen is a gas and it's N2 in its elemental state. All right, now if we have a monatomic ion, one atom with a charge, the charge is the oxidation number. So here we have chloride ion, Cl-1. All right, not in its elemental state because it's got a charge. All right, chlorine in its elemental state would be Cl2 anyway. We saw that earlier. Here is chloride Cl-1, oxidation number -1, because that's the charge of the chloride ion. All right, monatomic ions only. Polyatomics, all bets are off. In a polyatomic, every different element in that polyatomic ion is going to have its own oxidation number. Magnesium, all right, magnesium +2, all right. +2 is the charge, +2 is the oxidation number. So if you see a monatomic ion, charge is oxidation number. So now we get to the little more complicated part, and that is for a covalent compound or a polyatomic ion. The oxidation number is going to be the charge that the atom would have if it shared electrons. If we would have electrons shared equally. I'm saying this wrong. All right, I should just read the screen, but I hate reading the slide. But it's the charge the atom would have if the electrons, instead of being shared, were fully transferred from one to another. And so, in some way, it's a way for us to measure which atoms have the electrons and do not have the electrons in a covalent compound. Now, the important thing to note is that those charges, or those oxidation numbers, because in a covalent compound the atoms don't have charges, but they have oxidation numbers, which is our bookkeeping way of keeping track of how many electrons they have. But those oxidation numbers all have to add up to equal whatever the charge of that ion or that compound would be. So in water, the oxidation number of the two hydrogens plus the oxidation number of the oxygen have to add up to equal 0 because water has no charge. All right. Now, one of the things that we're going to find out is that oxygen is going to be our hero when it comes to redox. Always going to have a -2 charge. So, or not -2 charge, a -2 oxidation number. Sorry, I keep slipping back into that charge equals oxidation number. If it's an ionic compound, then it would be the charge on the oxygen atom. In a covalent compound, it's the oxidation number. So we're going to look at nitrate. Now, when we look at this, we have 1 nitrogen and 3 oxygen atoms. And you might say, okay, well, oxygen from the periodic table is -2 and nitrogen is -3, so I know, but it doesn't work like that, okay? Oxygen we'll be able to find that way, but nitrogen we can't. All right. So remember first, and our first step is going to be that all the oxidation numbers of all the different elements have to add up to be whatever the charge of that ion would be. So for nitrate, that's -1. So the charge equals 1 times the oxidation number of nitrogen plus 3 times the oxidation number of oxygen. All right. And all that's going to equal the charge. Well, we know the charge of nitrate ion is -1. We know that the oxidation number of oxygen is going to be -2. So we go through and we plug in the -2 for oxidation number of oxygen. We plug in the -1 for nitrate. Now you can solve that expression because we have one variable, and that variable, or one unknown, is that oxidation number of nitrogen. And you can solve that and determine that in nitrate, the oxidation number of nitrogen is +5, while the oxidation number of each oxygen atom in nitrate is -2. That's a key and important thing to remember, is that we're determining the oxidation number for each atom in that particular compound or ion. So each oxygen atom in nitrate is a -2. The one nitrogen in nitrate is a +5. Oxidation number, not charge. How about CO2? That's a neutral molecule. Neutral molecule has a charge of 0. All right. So now we know that 1 times the oxidation number of carbon plus 2 times the oxidation number of oxygen has to add up to whatever the charge would be, and well, the charge is 0. Remember, oxygen is our hero when it comes to redox, -2. So the 1 times the oxidation number of carbon plus 2 times -2 adds up to equal 0. So for carbon, carbon has an oxidation number of +4 in carbon dioxide. So the carbon atom is a +4 oxidation number. Each oxygen atom is a -2. All right. All right. So that's it with determining, oxidation number. Next, we're going to look at how do you take that and figure out what's oxidized and what's reduced in a redox reaction.